and gratitude towards the great scientists whose discovery we commemorate today. I request the respected dignitaries, Honorable Vice Chancellor, VC GP Rajshekar sir, Professor GP Rajshekar sir, our chief guest, Professor Ananta Ramakrishna sir, all deans of the all deans of the university, all principals and Principal College of Science and Technology, please, and EC member Sunita Madam, Professor Sunita Madam. I request all to come on to the dais to garland the portrait of C.V. Raman sir. Now we move on to our technical sessions. The first technical session today, we have invited talk by Professor Ananta Ramakrishna sir, the former professor of IIT Kanpur. Presently, he is the Dean and Principal of Githam School of Sciences, Githam University. And it is our proud privilege to welcome sir for this invited talk. Distinguished academician and administrator with decades of experience in teaching, research, and in institutional leadership. Now I request Professor V. Lakshmi from Department of Human Genetics to kindly give the formal citation and invite the speaker to the dais. Very good morning, Honorable Vice Chancellor, Sir G.P. Rajshekar, respected principal, all the dignitaries, faculty members, research scholars, and students. It's my proud privilege to introduce our speaker, Professor S. Anantaramakrishna. Professor Subramanian Anantaramakrishna, who is a physicist renowned for his contributions to optics, photonics, and the development of metamaterials and plasmonic structures. Professor Ramakrishna completed his MSc from IIT Kanpur in 1995 and earned his PhD from the Raman Research Institute, Bangalore. Following his doctoral work, he pursued postdoctoral at Imperial College London. In 2003, he joined IIT Kanpur as a faculty, rising to the position of professor, where he led a research group bridging theoretical and experimental studies in optics and condensed matter physics. In addition to his academic achievements, Professor Ramakrishna has held important leadership roles, including serving as director of the CSIR Central Scientific Instruments Organization, Chandigarh, in 2020 on leave from IIT Kanpur and served there until October 2023. Following his tenure, he returned to his faculty role at IIT Kanpur. In August 2025, he joined Githam Deemed University as Distinguished Professor of Physics and Dean of the School of Science. He has over 200 publications and more than 8,000 citations. His excellence in research has been recognized through numerous prestigious honors. He has been recognized for his outstanding achievements from an early stage in his career, receiving Young Scientist honors from the Indian Academy of Sciences and the Indian National Science Academy, and being named a young affiliate of the World Academy of Sciences. He was a P.K. Kelkar Research Fellow at IIT Kanpur and a recipient of the Swarna Jayanti Fellowship from the DST, two highly competitive honors awarded to promising young scientists. He later received the prestigious Shanti Swarup Bhatnagar Prize, one of the India's highest scientific award.
Invitation as well as the slightly the the introduction was probably more than what I deserved, but good enough. I mean, let me start. Yes, sir. So Professor Rajashekar, of course, I know him for some time, and we are from the IIT system. Okay. But today, on the National Science Day, when we remember Raman's contributions to science, and where most of us will be talking about esoteric discourse, would like to talk to you about. That is how to make money out of science. What I want to talk to you is how to make money for developing equipment. Raman developed a lot of his equipment. Still, there were expenses. There were expenses about consumables. There were expenses about visitors. There were expenses for everything. I think Professor Rajshekar will agree with me that expenses are all about it. And we are, as administrators, you are struggling to find money for it. When India became independent, government of India offered Raman. You have seen a gas light in the audience. Have you seen a gas light? Okay. What do you have? You have a burning flame, and on that you put something that seems to glow so bright. That's a thermoluminescent net made of a thermoluminescent object. It is usually uranyl hexafluoride that is used there, and that is what he had a factory making those because he knew about light, he knew about technology, he knew about science, how to make it, the chemistry, prosperous time of all mankind. We have never take you to connect few seconds. You talk here, your brother is listening to it there, 12,000 kilometers away, immediately. So in communications, in transport, in quality of living, in food, in medicine, in hospital treatments, everything, we live in the most prosperous times ever. And the reason is actually science. Science, which has undergone a transformation into technology and gives rise to products, that is the process through which we have become prosperous. And that is the process through which societies have become prosperous. You can actually use this opportunity in your lives to actually take your science to the market, and it becomes commercial, and it becomes something that can make you rich. Science can make you rich. We don't need to be, you know, every time we say, there was a teacher means you always imagine somebody who is coming very poor. We don't need to imagine that. Science can actually make you rich. So I will today talk to you about some three cases of technology development which I participated in, which was an effort from going from the lab to the market. And in all cases of entrepreneurship, technology development, there will be failures, there will be successes. So I'm going to share both with you so that you understand failures can also be very important. And the important thing is to do a failure analysis, whereby by doing that failure analysis, you understand how to succeed later. So whenever you are talking of innovation, you first have to do a opportunity identification. That opportunity identification, there are hundreds of opportunities, thousands of them. For any given problem, if you choose what is the problem you want to do, then you may come to a situation where you have fewer number of opportunities. So the innovation actually starts with identification opportunity. Sometimes we say in science, innovation starts with a scientific idea. No, actually, it actually starts with an opportunity identification, to which then you look at an opportunity selection through what are the ideas you have. So by the time you come from opportunity selection to from opportunity identification, the number of ideas that you can utilize, the number of things that you can do have already the number of possibilities have reduced. And it is these that you have to take forward and move to development and testing. Many of the ideas go out of the window. You simply cannot use those, they do not work. And it is very important to push those ideas through this window of development and testing. And as you go through the development and testing, you become far fewer ideas. And by the time you're onto production and launch, you have got the one hero that has worked. You got the one grand idea that has worked, that can work, and that can actually be commercialized. So it's a hard battle. You start with many and you come down to just one. And this is the problem with entrepreneurship. Why many of us don't try? We think that we will not be able to get to that one thing that is needed at the end. But the point I will make is, if you actually start with just one idea on this side, you will never get it through all these things. So on innovation is not about having one idea. It is about actually opportunity selection, identification and selection, for which you need many ideas to come together. And that's why you need multidisciplinarity and a very broad understanding of science. Now, I just described three cases that I participated in the commercialization. One was actually about a biomedical device, which is to have LED based blue light treatment for neonatal jaundice. The second one was about that was developed in the COVID pandemic by us at CSIO Chandigarh, which is to provide air sanitization possibilities. And the third one was developing stealth. When I say stealth, I mean radar absorbing and infrared emissivity coatings for materials which are used for ground equipment, ground assets. That is a defense application. So when I take the first example, what's the problem? The problem is jaundice affects many babies, newly born babies. I'm sure there will be many parents here who would have had babies with jaundice, or many children here who were born with jaundice initially. What happens? Baby is born, but the liver doesn't know. So liver has yet to start working. But if the liver is yet to start working, the hemoglobin, heme that is being broken down, generates bilirubin. Bilirubin keeps accumulating till the liver starts working to excrete it. So that bilirubin is a neurotoxin. So if its concentration increases, it can be damaging to the brain of the baby. It can result in long-term developmental problems as well. Even in extreme cases, even mortality can be there. So what do doctors do? They have to treat it. Now, one way of treating it, which is very effective, which is the most often used treatment, is to just subject the baby continuously to blue light irradiation. And how much is the light that has to be there? And there are norms for all those things. Now, when actually my son was born, and I had a problem in treating him, because he was perfectly fine from all perspectives except this. And when I was talking to the doctor, they say, oh, now all these units are in the NICU. So the baby will be away from the mother. The baby, it should be quite hard to manage. So I said, light treatment that I can do because I work on light. So I actually devised something and it was all acceptable. I'll talk more about it. But then we wanted to take, that is the beginning, selection, opportunity selection that happened. So I started moving out and seeing whether we can actually make such units easily available in public hospitals and so on. So what we did was to actually have a startup company under a faculty entrepreneurship of IIT Kanpur, and said that we will develop a low cost, maintenance free, compact phototherapy unit for bedside treatment, for any treatment. It is a very versatile unit that we started. But So to very quickly explain to you what is actually happening is this bilirubin, which is a product of hemoglobin breakdown. If you see, there are so many. I don't know. Can you see the laser light? I think it's a TV screen. It doesn't scatter. All right. So if you see, there are so many geometric and configurational isomers of bilirubin. So when there are so many geometric isomers and you're subjected to excitation by blue light, the molecule excites, de-excites, but goes into another configuration or another isomer. So this keeps happening till it goes into one isomer, which is called lumirubin, and that is excreted by, it is water soluble and excretable by kidneys. So there is one, the pathway by which all kinds of bilirubin convert to that particular isomer is not known. It's statistical, so it keeps going around, jumping up and down to different configurational and isomeric, geometric isomers, and then eventually it will be some of them will get into a lumirubin, and you take it up. That's the pathway. Now, when I look at this, however, at that time, 2010, 2009, most of the babies were being treated by blue fluorescent lamps. And what we did was, there was some anecdotal evidence that babies treated with CFL were more effectively treated in a shorter time. So that is where the anecdotal evidence had to be turned into scientific thought. So investigating the spectra of all these lamps, in fact, you will be surprised. The luminophores used in almost all the equipment is the same. And you found that there's a difference between CFL lamps and tube lights which are being used in the spectrum. So we identified one extra major illumination peak that was there in the spectrum. So from that, we moved into multiple introduction of multiple colors, multiple wavelengths in the phototherapy. We did experiments on the bilirubin in lab and found what was the yield into lumirubin, and we could actually optimize it. Then we went in for clinical trials with that kind of equipment that was designed. So this was the first unit I got built out of by a carpenter in my home. That was my child. Later on, they became more and more sophisticated. We started taking patents and copyrights and so on. But eventually, these were the kind of units that we went in for clinical trials that were handed over to the Kanpur Medical College and to two different hospitals, private hospitals, and we commenced our clinical trials. Net of it, all of it, what I would say is eventually the clinical trials showed that our treatment was 40% faster. The clinical trials were unambiguous about it. We had a control, we had where they were treated by the normal things, and we had this where they were treated by our systems, multiple wavelength phototherapy, and this was 40% faster. That is, if you're a normal, if some baby takes usually 5 days of treatment for that level of bilirubin, in our case, they would take hardly 3 days. So it was better than what that much. So these were completely designed to be operational in NICUs, in bedside. They were supposed to be all kind. You could do almost anything with them as far as this treatment goes. But what happens? Clinical trials, we were successful. We were doing good science, great technology, but we didn't. We had zero sales, and we closed down the company in 2003. It was a commercial failure, and the commercial failure happened because of its own reasons. We were not being fast enough. We wanted to launch in 2019-20. COVID came upon us on our launching period. In 2 years, everything changed. Then the bill for medical devices regulation came, and then we were now supposed to, in spite of having done the clinical trials, etc., had to go back to the CITESCO for medical device approval and so on with COVID and so on. So we eventually gave up. Because the business environment had completely changed. What was really the failure analysis? We just took too long. We were all professors who were like, we are all part of the same thing. We sit down and say, okay, aaj nahi work, kal karenge, we will do it tomorrow. It's okay. How does it matter? like our PhD students work, no? Sir, I'm going tonight. I'm not in the mood to do the work. Okay, better go home, come back tomorrow. So if you are relaxed like that in commercialization, what happens is this: your company closes down. It was a lesson we learned. Then my second major experience in a major commercialization was when I was the director of CSIR CSAO in Chandigarh, and COVID was upon us. The government of India said, CSIR, come on, do something about it anyway. So first of all, what we did, we said, okay, we have to find out the nature of COVID. So CSIR actually did sampling of air across many places, hospitals, patients' homes, auditoriums, trains, buses, etc. We at CSIO developed the air samplers for CSIR. And using these air samplers, these studies were done. CSIR IMTech and CSIR CCMB at Hyderabad, they did the studies. And for the first time, we declared to the world that COVID is airborne. It is not conveyed by touch of surfaces, contact surface. It's not a contact driven thing, it's airborne because we could find the virus everywhere in air. No, that was very important. It was India was one of the first countries to actually declare that. The WHO was still insisting for 6 months after we declared, 6 to 8 months, that it was still borne by contact, not by, it was not an airborne disease. But that apart, once we knew that it was airborne, what do you do about it? That was the question. How do you create safe places? Let's say you have this auditorium, there are so many of you. How is this auditorium going to be a safe place? How do we reduce the amount of transmission, the proper probability of transmission among the people? You're going in a bus, you're going in a train, you're going in an aircraft, you're sitting in halls, you're sitting in offices, in malls. The air has to be kept sanitized. And how do you do that? So the most important thing was there was no time to do any new research on it. The pandemic was upon us, and we wanted a sure short solution. So what did we say? I said that, okay, I know ultraviolet C light destroys virus, and that we known for about 100 years. And it is the only foolproof method which you can use. But I cannot put ultraviolet C lamps here because that would damage our skins, our eyes. It is carcinogenic. So it has to be done in a safe manner. So that was the question: how to do it safe? Further, the solution should be inexpensive. It should be a retrofit. I cannot say that you please, COVID has come, so please replace the entire AC HVAC system here. I cannot do that because it's too expensive. It cannot be implemented. So to be implemented, it had to be an example of frugal engineering, and that's what we went right into it. Uh, See, first of all, we needed to know how much ultraviolet was needed for the COVID. So, in a unique example in the world, within the BSL 3, Biological Safety Laboratory Level 3, which is where you can do experiments on such diseases, CSIO built a chamber inside the CSIR IMTech BSL chamber and said, we give you a possibility of understanding how much UV light should be there. And at that time, there are a lot of claims. There are people saying you can use a negative ion plasma, you can use essential oils, you can use herbal oils, something to do with Ayurveda, something to do with traditional medicine. There are all kinds of claims that you can clean up the air like that. So all of them had to be tested, right? So we created a chamber where you could test for any of these things by changing their parameters. It was a very, very flexible chamber. What we developed, that is actually shown here. And this chamber, you could pump in, IMTech had live virus, live COVID virus, which they have cultured from many patients. IMTech is a place of repository for all viruses and bacteria. So they actually cultured the virus, and we would spray in a live viral culture into that chamber. And that chamber would then be, you would use whatever protocol you want to try out and test it. And finally, you would sample the air inside the chamber and see whether the virus that you collect there can infect other cells. So using that, we actually established how much ultraviolet is needed, how much dose is needed of the ultraviolet. And eventually the chamber would be sanitized entirely by ultraviolet. That was the protocol. So we had to go through standardizations, we had to get certifications for all kinds of things. And you see, when you make a device, remember, if you're trying to commercialize it, you need certifications of every kind: electrical certification, safety certification, environmental certification. You need the purpose certification, like in our case, how much light is there, whether how effective is it against the bacteria, against the virus, or whatever. So all that was done, and believe me, it was all done within a period of 2 months. We really can work fast when we want to, when we need to, and we actually succeeded in that. COVID taught us that. So here is an example of our solution. If you have a duct, let's say this is a duct that is going that way, all right? Air duct. You have air duct coming in above. So you actually do a very frugal innovation. You have these trays containing UV lamps, which you just cut a hole in the duct and you can actually retrofit these trays into it. It is a very, very unique solution that was developed, and every kind of simulations, airflow simulations, everything had been done within those systems. So it was a solution of air sanitization for such closed ventilation systems. So you clean up the air that comes in, make it free of virus. You're taking in air from the audience, and when it goes into the mixer and comes back through the duct, it gets cleaned up. So that statistically, you're reducing the amount of virus that is there in the air by continuously cleaning it up. It is not possible to throw out all the cold air because then the HVAC system will not work. The amount of thermal demand will become so much it will stop working. If you put HEPA filters into the system, your pressure drop is so much the AC system will stop working. So this was the only solution we could actually come up with, which actually addressed everything. So it was implemented in various kinds of buildings by us itself. As an example, this technology was given to something like 56 companies, including very famous companies like Voltas and Paras Defense and so on. They all implemented it in various places. So I'm sure you all recognize this building. It is the old Indian Parliament. At that time, we were asked by Government of India come and implement it for the Parliament because the Parliament is in session. What we did was these ducts. They look like passages, entire passages, but those are actually ducts, air ducts of the Parliament building. They are so big you can just walk across 4 people abreast. There will be no problem. So these are all the systems that were placed by us in the duct to give it the correct level of irradiation so that the air is completely sanitized by the time it goes through. It was implemented in the Central Hall, Lok Sabha, Rajya Sabha, all those. We developed something for Indian Rail, the new HVAC system of RDSO. RDSO has approved our designs and put them into the RDSO designs. So all new trains are coming in with that. All the Vande Bharat and all those trains actually contain these systems. So going by railways is actually much safer. Why? Because railways said even after the epidemic was over, they said whenever in any region we find that there are a lot of cough and cold or fever and so on, we switch on the systems. So actually, the going by railways is much. Did it in UPSRTC buses as trials. These buses have run lakhs of kilometers. There were units like these which were developed for rooms without HVAC, where air comes in, it is sanitized and pushed back, and classrooms and so on. We can use those, and lots and lots of designs were developed. Lifts in Bombay became a particular point where a lot of transmission was happening. So very compact units like these were developed. They were put up in various places, and Voltas took it and implemented it across many Tata projects. Railways also implemented it in the toilets, but then they stopped because the cleaners would hose it with water. So, they would stop working. So commercial things are always like that, where you some things that can't be planned display amazing properties. Turn it, you use its geometric shape to create resonances. You see, if you take a have resonances, those electromagnetic resonances are utilized by me to create media where light can do many very strange things. Depending on the size of these objects that I do, the medium, the metamaterial can work brilliantly in the RF, radio frequencies, microwaves, or at infrared frequencies, whether the sizes are or in nanometers. So I have worked on all these skills. But the most important thing is, uh, we by chance I described the situation. We had a complete understanding of the systems. We were working with DRDO for certain stealth development of stealth materials for aircraft which can be stealthy, not be seen by radars. But at that time, we realized that we could actually develop a completely different system. And that we have called it a multispectral surface cloaking system. And the commercial name is Analakshya. Analakshya means something without a target. It is not a targetable object. So it is safe from attack. So let me very quickly say that in military, stealth is very precious. So precious, very strange shapes. Some of them are not even aerodynamically good. Like that was the first aircraft that was developed, and aerodynamically it's a very poor aircraft. Still, stealth is so precious. U.S. Air Force developed it and said that we want it. They are still flying. Later, we realized that it did aerodynamics and the shaping does not need to be done so differently. No, but it's very, very expensive. Now, what does the stealth material need to do for an aircraft or anything? That you don't have to reduce the microwave reflection back to a radar. You have to create absorption of microwaves on the material. You have to reduce the infrared emission of so that it does not you cannot see it on these night sites. You call it infrared sites. Infrared cameras are there which see in the thermal infrared or in the mid infrared. So you should not be seen there. So you have to control the infrared, and you need to blend the near infrared or optical paint to match the background. That's why these aircraft, stealth aircraft, are mostly used for attack at night. So they are painted blackish. Their paints look black. So overall, these are some of the requirements. And where can you be seen? Wherever the atmosphere allows you to see far. If you in the visible, yes, you can see the blue sky. You can see 20 kilometers, 30 kilometers, before which the haziness of the atmosphere does not let you see accurately. If you can see here in this region, you have the infrared gaps in the atmosphere, so you can again see about 20 kilometers, 25 kilometers. Here you have the RF, it's very transparent. So you can see very far distances, 300 kilometers, 400 kilometers, you can see through the atmosphere in the RF. Because the atmospheric fluctuations do not affect the microwaves with much larger wavelength so much. So you need to make your system, if you're going for stealth, effective in the visible, the infrared, and the microwaves. It's not one band. If you want, you have a spectrum. So challenges that have come for grounds of trucks, of tanks, your missile systems, so on. You have the requirement. You can see from space. Yes, this is an image from space. This is an optical image on the right hand side. You could always see, you all see the Google Maps. You can see from space how things look. But then remember, you can see from space only if it is daytime, or if it is not raining, or if it is not cloudy, or if there is no fog, there is no haze. Otherwise, most of the time, my wife was here for Karwa Chauth and she could not see the moon because it was all hazy. So becomes like that. You can't see anything. Right? Now, whereas if you actually use radar to see and you synthesize the image, this is by a technique called synthesis aperture radar. synthetic aperture radar, you can actually see almost as well as the optical images are. You can see the individual trees, you can see the roads, and if there is anything made out of metal, you will see it extremely sharply. So today, it is almost impossible for ground systems to hide on the battlefield. Everything gets seen. There is no possibility of hiding anywhere on the battlefield. Everything is seen. Everything is seen. You need to do most of these radar cross section reduction schemes. By that I say that reflection from of the radar. By that I say that reflection from of the radar should reduce. We call the radar cross section. So you have to reduce the radar cross sections for all the objects that use on the field. But on the field, you can't do that because your tank can be going this way one day, another direction another day. Radar cross section may be low from one side, but it's not that your enemy is only seeing from that side. The enemy may see it from any direction. Satellites are going overhead. They may be off in angle, in axis. So your ground systems need protection all around, 360-degree protection. So that becomes the greatest issue of how to reduce the radar cross section of your ground system. And the only way of doing it is you have to reduce the reflectivity of the surfaces by which your ground systems are made. And what are most systems made? What's a truck made out of? Steel. What's a tank made out of? Metal, steel. Everything is made out of metals. And metals reflect microwaves or radar waves very, very strongly. So everything can be seen very well from space or from an aircraft using the radar. So the challenge is you need to make those systems absorbing, or you need to cover it with something that is absorbing. And that same absorbing radar absorbent material has to also have low infrared emissivity, match the optical background, etc. So traditionally, what do people use? You might have seen, no, if you go around the army cantonments and all, you will see some cloth that is hanging that is colored, multicolored, and with all kinds of awkward designs. That's to actually change the shape. Actually, you start from a distance, start not seeing the shape of the object that it is covered with. So that is the optical pattern matching that you are doing. But those also have infrared properties, actually, which you don't see with your eye, but if you used a night vision camera, you would see. But those objects, those cloths also have to be radar absorbing. And this is a challenge that people have had in the field and nobody could solve it for a very long time. I mean, it's just an unsolved problem. When somebody pointed it out to me in 2016 in RCI Hyderabad, said that it doesn't work, these things don't work. So I said, let me get it working. So how I could get it working, I'll just see. So we have something called metamaterials. These are, as I told, structured designer materials. This is an example of that where, or this is an example of these. These are like printed circuit boards, these, which you actually create electric and magnetic resonances on those so that you create a fantastic absorption. For example, if you see here on this graph, you get very high absorption, let's say at about 10 gigahertz on this structure, and that is happening because of the simultaneous electric and matched magnetic resonances that are there in the system. It's an electromagnetic resonance which you are using to absorb effectively with perfect impedance matching. Now in IIT Kanpur, my colleague Professor Srivastava in the electrical engineering and I, we started working on this. And by 2014, we had got really broadband absorbers. And the radar absorber has to be broadband because you don't know at what frequency your enemy is watching. It could be any frequency where the atmosphere is transparent. Or there are other practical requirements due to which frequency can be down. But we probably could actually absorb most of the radiation in, let's say, 4 to 18 gigahertz. You could absorb it totally and completely. So you could do that. But then these were like circuit boards. You can't take a circuit board and put it on a tank, can you? So we actually developed for these purposes some things not out of circuit boards, but out of printed inks, out of transparent conductive oxides, depending on the applications. They could be flexible, they could be anything. We were doing it, and then we decided to we were very successful in that. So what we want to do is we want to develop cloth which could allow people, tanks, vehicles, air missiles, everything to hide from the enemy radar. Kargil and other places. Various defense services and national agencies to do the testing anywhere and everywhere where we could actually enable, which enabled me to determine that yes, with these objects I can hide these, with these systems I could hide the system, these vehicles and so on to various extents of efficiencies. So what happened? The commercialization aspect, if you come, what did we do first? We developed it in 2018 and we filed for the patent in 2018. It was granted eventually in 2024. It took 5 years, but we had protection from 2018. It, we published actually after later, much later, aspects of this development. Then in 2022, an exclusive transfer of technology was granted by IIT Kanpur to a company and for the manufacturer and other things, further development of the product. Because when we developed it, it was a product which works, but it is not a product that is customized to the individual requirements of the customer. Ruggedized, you need to be made cheap. I mean, you have to they have something called, you can trace their standards back to the origin. All those things are there. So one single product like this for the defense needed 50 certifications, 50. And this is something that actually takes a lot of time and expense, which commercialization you should always include in. You should not think that that's not my job. If you don't do it, you don't get it done, the product will never take off. Finally, the first order from the Indian Air Force is being implemented even as we talk. I cannot tell you more about it, but we now there are future projects which are ongoing, which are a variety of products that are there. Let's say Kavach for tanks, for trailers, for tank trailers, for many things. All these kind of systems. The S-400 system, which was the hero of the Sindur operation, did starting from developing the idea in the laboratory. So this is a product that was whose idea started in India inside the laboratory, whose proof of concept was made, proof of principle was tested. We went on to actually developing functional prototypes, field demonstrations, technology development, production enabled, and all the entire process has actually it has gone through. And that is a great triumph of Indian science in this particular case because we actually give invisibility to the military to a certain extent. Okay. So with that, I will stop here. Any questions are welcome. Let me answer that question. See, the photochemistry of the bilirubin has still not been established to the level of understanding that we would like to. In fact, extensive studies like this have to be acoustic metamaterials that have been developed that are being tested and tried out, but not, as far as I know, nothing is yet functional. In other countries, they are trying it out. It is not yet functional even there. Because for sound, you have very nice normal materials that have been actually tested and certified and that are available. See, the problem about military technology is that you need to have something that definitely works. So the development cycles are very long. And so far, when the development attempts are there, I know they are not yet been implemented for sonar. But the radar frequencies, yes, there is a lot of requirement, but the requirements are very different because the user requirements are very different. See, for ground assets, if the ruggedization is needed of a different kind, it should not tear and so on and so forth. For underwater, the requirements of are different.
we move on to the next technical session. This session, our speaker is Professor Abhijit Mukherjee from Department of Geology and Geophysics, IIT Kharagpur. Professor Abhijit Mukherjee, sir, is a renowned expert in geosciences and is more than 160 peer-reviewed journal articles. He served as editorial role for the Journal of Hydrogeology, Applied Geochemistry, Water Resources Research, Sustainable Geoscience and Engineering, Environmental Science and Technology letters. Professor Mukherjee has widely worked on geological and human resource pollution and water quality estimates, including application of advanced computation and artificial intelligence techniques. For his work on groundwater, among several accolades, Professor Mukherjee has been confirmed the National Geoscience Award, that is the National Mineral Award, 2014 by the President of India. The IAGC Karaga Award to 2020, the AGUBL Medal 2023, the GSA and IAH Applied Hydrogeology Award 2025. He was introduced, inducted as a fellow into the Royal Society of Geochemistry 2020 and Geological Society of America 2021 and the American Geophysical Union 2023. He was awarded the uh, Sasti Swarup Bhatnagar Prize in 2020, regarded as India's highest science award. Thank you very much.
Morning. Now, since yesterday, I have been enlightened with a lot of different topics, and this is possibly a topic which not a lot of people care about. So I thought this would be a good topic for this occasion. I really thank Mr. Rajashekar, your DC, who has been a senior colleague to me at IIT Kharagpur, and who kind of really is good to be here today. So I'm really thankful for this invite, and I'll go ahead and talk about how groundwater security of South Asia may be viewed from the angle of science as well as human practices and policy interventions. Before I go in, thank all these organizations who I've worked with for the last about 20 years, and many of the contribution of our colleagues, individual slides. I thought them of putting individual slides. I thought them of putting in one slide together and talk about it. Now, I'll be talking about groundwater. Now, this is something that many of you are aware of, and we think that this is a topic that has been a 20th century thing. In the newspaper, and I looked at some parts of southern India. I don't know. I'm not going to that debate. However, in the history of India, there has been enough examples, starting from the days of Indus Valley to the modern days, and you have seen that groundwater has been explored to the subsurface and has been given out to the people. And this starts from the city of Mohenjo-daro, which is known as the city of wells, and even like about 5,000 years from today, 5,000 years back from today, people were using this. However, in modern days, in modern days, this is not just left with personal uses. And the use of groundwater has been in food production, for of course drinking and commercial purposes, but also in the use of groundwater. Now, what are the groundwater issues? So, of course, we'll be talking about the science a little bit, but let's the issues like why should we be here to even listen about you? some of this flooding caused by groundwater. So water scarcity and water excess can go literally hand in hand, telling you that it is more of a management issue than a science issue. So we need to understand that perspective too. I mean, as much as we are exploring science as a scientist, we also need to understand the human angle and the human management. And otherwise, if you have water scarcity or water excess, we are looking at drinking water security issues. And this is for us, as well as drinking water security issues. And this is for us, as well as for the animals which we have domesticated and who heavily dependent on us for their survival. But just the quantity is not enough, and we also need to understand the quality of groundwater. And this is where you need to worry about quality or the chemistry of groundwater. So what do we work on? I had the physics talk yesterday and the chemistry talk yesterday. We are work on both the physics and the chemistry of groundwater. This is, as I teach my students, the physics and chemistry are actually two sides of the same coin. Looking at, it's not, I didn't take it from Google. I shot it myself. And these are photographs from people across this country where people are just drinking bad water. Not necessarily they have done something bad in this life or the previous life. It's just that they are drinking bad water. And let me tell you, and let me tell you know, as per the session, 60% or more of the health issues and death, untimely death that happens in the world is actually because of water pollution. So water pollution has a lot of impact on a society level that we don't appreciate. And then we have something called the climate change. Again, I doubt that how many of us really understand that. I had the opportunity to work with the best in the climate science in the world. However, I'm still at a loss, like if we really understand it. However, one thing we do understand that if climate change is happening or would be happening, one of the first impact of climate change would be hydrological cycling. So all these problems that I showed you in the background are not going to go out, get accentuated in the years to come. Not too far, maybe 10 to 30 years. And all these problems will possibly magnify in different levels. And that's why you need to understand it. And this is more true when we're looking at the present decade. This is what we call the decade of UNSDG, achieving Sustainable Development Goals. As many of you might be aware of, by 2030, we're supposed to attain the UN SDGs, the 17 goals that has been identified by the United Nations, which we should be attaining um, as a human race, irrespective of caste, creed, religion, nationality. We should be all attaining these 17 goals to a better time. And goal number 6 is specifically on access to clean water and sanitation. So to do that, we need to understand groundwater because groundwater identifies 99% fresh water that is available on Earth's surface. In India, if specifically take the case of India or South Asia broadly, we have a scenario. And this scenario possibly has been happening for some time, but it was only identified about 15 years back in 2009. And based on a couple of studies, we found out that the groundwater resource in India, in South Asia, is dissipating in a very fast level, fastest in the world. And that's what us scared. And since then, there have been numerous studies, numerous media reports, and I'll try to show you some of those. So what we do in our group and what we study in my extended group is we try to answer a very simple question. We try to understand how much safe groundwater is available in South Asia and what is the future. Very simple question. However, of course, the details has the complexities embedded into it. And because just not having groundwater is enough, you need to have safe groundwater. So why is it an emergency in South Asian context? Well, the reason is that the South Asian region or the Indian subcontinent region occupies only about 3% of the global terrestrial land. Only 3%. However, about one-fourth of the global population and one-third of the food production actually happens in South Asia. So you can imagine that if you have just 3 to 4% of the terrestrial land kind of hosting like one-fourth of the global population and providing the food, one-third that is produced in this planet, that cannot be a sustainable practice. Consequence is that we are the largest consumer of non-food in this planet. These estimates from a couple of years back, it talks about the maximum groundwater user in this planet. And they have listed about 67 countries. And as you can see, we have India out there, and the groundwater consumption by India is the largest as much as of the day and possibly in the near future too. How much? Well, if we add the second and the third one, which is the US and China, we are still ahead of that. So we are actually consuming the largest volume of groundwater in this planet. Uh, this is not everywhere. If you look at these maps, the two maps, um, the first one, it shows the extent of the irrigated landmass, like where food production happens. And you see, like, there are all these colors on the left hand side, and this color has red and scarlet, which are the largest volume of irrigation that happens from groundwater. And there is one place on this planet where this is consistently high, and that is in the North Indian plains. And within the North Indian plains, again, there are, there are divisions, and maximum groundwater is used in the Punjab Haryana region and the Bengal and Bangladesh region. This is where the maximum volume of food is taken out for food production and also as a little bit. And together, this area provides the largest amount of food production in this planet. Consequently, India is the largest user of groundwater, not just today, but in the human history. No time in the past or possibly future, any other country using this non-renewable geological resource is extinct. We need to understand that. And to do that, we need to come back to geology. Because this is to make the floodplains. This is the floodplain, one of the largest in the world again, and um, together called the IGBM, and um, together called the IGBM. It provides the largest repository of the groundwater in South Asia and one of the largest in the world. Whereas this dark blue is what we call the Tectonic India, Builder rocks of India. Why is this important? The reason it's important is that light blue India, the IGPM aquifers, host about 75% of the groundwater resource of this country. Whereas it occupies only 22% of the landmass. The dark blue area, which is the Tectonic area, which also includes parts of Andhra Pradesh, um, actually covers area which is about 60% of the terrestrial land of the Indian subcontinent, whereas the groundwater resource is less than 20%. So it is, as you may understand, it's a very polarized distribution in a very geographically protected areas. So these North Indian plains of the IGBM aquifers are the largest repository of groundwater in South Asian region. However, there is also a problem. If you look at the map at the right, you'll see that these IGBM aquifers are grossly polluted by geogenic pollution. And this pollution includes arsenic, fluoride, and it is also present in Andhra Pradesh, as you can see the yellow patch down in the south. Um, you also have these blue colors, which indicates arsenic, and they are mostly present in the IGBM areas. So between the fluoride and the arsenic, much of the groundwater that is present in India are actually polluted and not suitable for direct human consumption.
Now, this technical session starts with a exciting lecture from Quantum. It is our pleasure to hear from Professor Vituri Srinivas, Department of Physics, IIT Madras, who will speak on quantum phase transitions. May I request Professor Manjulata Madam, Department of Geology, to present the citation and invite the speaker.
Good afternoon, all of you. So I'm thankful to the organizers for giving me this opportunity to present the profile, that is academic profile of Professor Vituri Srinivas garu. So first of all, I will start with his studies. That is, he started during 1982 to 87. He went to IIT Bombay for his graduation, and after that, in 1987 to 90. He went to Canada for postdoctoral fellow in Dalhousie University. So after that, 1990 to 92, visiting scientist, Tata Institute of Fundamental Research, Bombay. That is, he came again back to India and joined there in Bombay again. And 1992 to 95, this is what actually he started his like a teaching profession as lecturer, Department of Physics and Meteorology, IIT Kharagpur. So he continued there and promoted as assistant professor in 1995 and promoted as associate professor in 1999. Then associate, that is associate professor, and after that he became professor in 2004 and continued till 2010. Then he went to this is IIT Madras. He shifted to IIT Madras in 2010 as senior professor and continued till 2025. That is last year he got retired. This is all his teaching profession and all. And now coming to research areas. So Professor Srinivas sir, he worked in research areas of magnetic and electrical properties of alloys and compounds, then disordered and nano structured materials, low dimensional materials, then thermoelectrics, that is pseudo gap engineering. And these are his research areas. Then coming to projects, he has taken up 17 sponsored projects and he had produced more than 200 publications and guided 20 PhD students. Then coming to membership in professional bodies. So two professional bodies, one is Magnetic Society of India and then Materials Research Society of India. Then finally coming to the visits abroad during September 1999 to December 2000, that is for 16 months. So I'm very much thankful once again to the organizers for giving me this opportunity. Thank you very much.
It's a pleasure to welcome sir to deliver the lecture.
Thank you. Uh, Thank you very much for the introduction. And I think I would like to thank first. Would like to thank Professor Rajshekhar for inviting me to speak about my work here. And also, I would like to thank organizing committee for giving me the opportunity to just briefly tell about my work. So, with this today's work, I'm going to talk about very simple thing that is phase transition. I think most of you know what is phase transition, and some of you know what is quantum phase transition. So, I want to give something for some students. What is quantum phase transition? This work has been done recently in 2024, and two of my students have submitted this in this. Now today, what I am going to do is first, what is classical phase transition? I will discuss. All of you know that one phase to other phase, when a material changes to one phase to other phase, then we call that is a phase transition. For example, if you know that the water at 0 degrees Kelvin is ice, it will form at 0 degrees Kelvin or 0 degrees centigrade, it will be ice. And at room temperature, it will be a liquid water. So ice means it is solid. When you heat that, it will become a liquid. So one of the questions, if you ask some of the scientists, why the at the 0 degrees Kelvin, what is the reason it is stable in solid form, and what is the reason at 300 degrees it is stable in water or liquid form? The answer, people who know vehicle is disorder. Disorder means, suppose if you make any material, let us say just now I said the ice. Ice has certain disorder. Uh, or any material if you take, for example, if you take iron, piece of iron piece, then you will have whatever inside the material. So this disorder is called punch disorder. That disorder you cannot remove. Even if you make a single crystal, there will be some defects or disorder inside. So that is what we call punch disorder. That amount disorder, whatever the inside is in perfect material, there will be a phase transition. Whereas in our materials, like for example, ice and water, I said, there we are also introducing disorder, but we are using a heat, thermal energy. We're using thermal energy to move from ice to water. So there is thermal fluctuations which lead to this transition. So these are the transitions briefly I will talk, and how to identify the transition. Transitions are also, there are phase one or the order one, order two. Some of you who have done the thermodynamics classes, you will know first order transition and second order transition. So these transitions, how they can be identified. That's what I'm going to discuss. So briefly, I talked about this, and then these are. No, after this moving, it's not moving. Okay. No, now I'm going to give the brief introduction I will give, and then I will discuss first what is classical phase transition, and then what are the magnetic phases. Because the phase transitions generally can be observed in magnetic materials. So I'm going to introduce a little bit about the magnetism. So the quantum phase transitions are generally observed in magnetic materials, superconducting materials, and ferroelectric materials. You can see all these wherever there is a transition, type 2 transition there, or second order transition there, those materials you will see that this kind of quantum phase transition. Okay. Then I will show the experimental results and then do the summary. And just now I said that the magnetic transition, phase transition, this is what the water here. And if you freeze the water, it will become ice solid. And then if you heat the material, then or sublimation, then it will give water, the gas. So these are the which we generally see in the nature regular light. These are supplies of energy from outside. Then you get this kind of transition. And the top arrow says it gives away the some energy while making the transition to other phase. So this is the typical PT diagram. That is P is the pressure and T is the temperature. When you take a material, let us say some solid material at temperature, room temperature, and start heating that, then what you will have is after some time there will be liquid, and then if you apply pressure on that, then it will become solid. So here it has gone from the liquid to, you cannot go back, you won't be able to go back. Okay. Now here, when I supply the heat here, then solid is becoming liquid. Then this liquid again becomes solid if I apply pressure. So therefore, there is a Gibbs free energy, H is enthalpy, and T is the temperature. That is the Gibbs free energy, H is enthalpy, and T is the temperature, S is entropy. So when this energy gets minimum, goes minimum, then you get the either solid form or liquid form. Goes minimum, then you get the either solid form or liquid form. So initially when it is T is equal to 0, temperature T is equal to boiling temperature, and if I keep the thermometer there, and what you will see is that near the boiling temperature there will be a significant disturbance or disorder. And this disorder is because of entropy. This entropy increase in interest. So there is order of disorder is nothing but entropy. So the entropy, you see that near the boiling temperature, the entropy increases, entropy of the liquid increases, and that is what we call transition temperature. And beyond that, it will be same. And this is one of the methods to detect the transition. For example, now let us say we generally use that the what is the boiling temperature of water? If you ask immediately, you will say 100 degrees. How do you detect that 100 degrees or not? So just by not by putting on a fan, but you have to measure the entropy of the material or latent heat of the material. That is how experimentally you measure, and accurately you can measure the temperature of the boiling temperature or freezing temperature of the of the particular liquid. Now I keep the temperature here constant at the boiling temperature, and then I measure in the time what happens to the time dynamics. I will see that means with time what is happening. So initially when I the liquid initially to the temperature will increase to certain distance, certain time, and then it will be flat. There won't be any increase, but you are still applying the heat energy, but that is still it is in the flat region. So after some time again it will increase. This flat region, what happens is in this region, why the temperature is not increasing is that energy, whatever excess energy is there, that is used, consumed for decomposing the molecules, water molecules into vapor molecules. So this is called latent heat. This is called latent heat. That latent heat we can measure by measuring the specific heat of a material. Suppose now you take a solid and if you measure the temperature, latent heat, then you will see what temperature. This is the typical diagram for the temperature versus pressure for the water. Initially it is here it is solid state, and then it becomes liquid, and then you have gaseous state, and gaseous state to liquid state we discussed just now, and then you can also have liquid state to gas state. So you will have a triple point. In this point, at this point, all three phases will be present at that point. The triple point, and in critical point you will have gas and liquid will be in same phase beyond that critical point. So now I will show something. What are the features of the first order phase transition? I said the classical phase transition has two orders. First order is these are the features you observe. One is discontinuity and the phase mixture is present in first order transition. Always in the first order transition, phase mixture is present, and these are the two qualities which are which are very important to say whether it's the first order or second order. In second order, you will have this. I have given an example of magnetic phase transition. Here, we have a magnetic material, And when you heat the magnetic material, ferromagnetic material, at particular temperature, it becomes a paramagnetic material. That means it will not be attracting with the with magnet, pure another magnet. So at below Curie temperature when it comes, then it gets attracted. So that kind of transition is called ferromagnetic transition or second order phase transition, and it is continuous and no latent heat in this, and there is no phase separation also in this. So now, can you play that? So in the first order transition, you will always see there is a jump, and then there is a in specific heat you will see the peak. There is a specific heat at constant pressure. These are the typical characteristics of entropy, and then there is a break. And this solid cubic material, and if you heat or if you do something, then it may go into external state or another different state. So that kind of transition is also called phase transition, which is a you can say the second order phase transition. You can measure the specific heat and all, and you can show that it will be second order transition, phase transition. And in ferromagnetic material, and you must have heard these kind of materials. There are ferromagnetic materials there in your twist and other things. There in your twist and other things. This is the structure of the magnetic moment inside the magnetation, total magnetation will be zero. And there are ferromagnetic materials which are the other arrows, if you see this arrow is slightly intense and this arrow is less intense, second one. So if you have that kind of arrangement, there is a net magnetation. Net magnetation because it is a phase transition from this state to this state because here a phase transition from this state to this state because here magnetation is zero, here magnetation is not zero. So if you have a finite magnetation and if you go to zero magnetization state, then what you will see is there is a magnetic transition, which you can say can detect. It can be a second order or it can be a first order, depending on various parameters. I will show you how to determine this, uh, the phase transitions. These are all classical. I am discussing only so far. So of course, this magnetism OT. So the change in flux is induced EMF. That's go to non-magnetic material. What are the changes you see? Different changes you see in the material. So if I take non-magnetic material and if I add, let us say if I take copper, gold, these are non-magnetic materials, and the magnetic materials are iron, nickel, cobalt, such kind of things are I've shown in my previous transcripts. They are generally the magnetic materials. So let us say I have big chunk of about 1 million atoms of copper atoms in a matrix, in a lattice, and if I add only 50 atoms of iron, 50 atoms of iron, that's what we call 50 ppm. That means parts per million. That means 1 million will have only 1 million atoms, only 50 are magnetic, remaining are non-magnetic. So now, if you take that kind of material, there is and measure the magnetic properties and electrical properties, what you will see is the Kondo effect. Kondo effect is there is one transition where you can see in both magnetic properties and electrical properties that is different magnetic. Show that those are the magnetic atoms, remaining are all non-magnetic atoms. So this is called a spin glass. And if you have small clusters, spins are forming in the form of clusters, then this is called cluster glass. That means they are placed, they have significant magnetic moment. Here only one magnetic moment. Here you have a 9 4 magnetron or something, 9 magnetic moments you have. 9 unit of 9 you will have. So there are clusters like this. And if you do the magnetic measurements on this, you will see the difference between that and this. The spin glass and cluster glass, there will be different. And then if you further go into the higher concentration of iron, then what you will see is the micromagnets, that is still bigger clusters, and there are super paramagnets also you may get. So there are bigger clusters you will have. And finally, this is the long range order, that is magnetic order you will see, that is called ferromagnetic order. So the ferromagnetic order you will observe at something like 17%. 70, suppose if you have a copper or something, if you put this 17% of magnetic atoms in that, you may see this ferromagnetic characteristics of the material. Ferromagnetic characteristics, how do we see? If there is a spontaneous magnetization, without applying the magnetic field, if we have a magnetization, then that is called spontaneous magnetation. So if you have a spontaneous magnetation, then you will say that that is a ferromagnetic material. Okay. Why I discuss all this is, but here in this region, about 10% to 17% region, you have interesting phenomenon, which is just now I said the super paramagnetism, and you have super spin glass. You have also spin fluctuations. Spin fluctuations means the spins are free and they can fluctuate because of thermal vibrations. Otherwise, if I have shown the ferromagnetic material, if their spins are very close by, then this spin will not allow it to allow this spin to move because there is exchange energy which is very very strong, so they cannot move. But if they are isolated, then they can move. Thermal energy can make them move in random direction. So, so the spin fluctuations are very very important in the magnetic transitions, and then you will also see non-Fermi liquid. See, conventional materials, if you take a copper or silver or something, they behave like a Fermi liquid. Liquid means liquid flow, you see, smooth flow will be there in the liquid flow. Similarly, electrons through the copper blocks, they flow smoothly without any problem. But if there are some hindrances, some voids or something like that, then you will have a non-Fermi liquid kind of behavior. But generally in metals, we see that Fermi liquid behavior. If suppose some solid physics people are there, then they will recollect that the free electron theory tells you how the electrons flow to the material. So the quantum that's what in this region also we observe the quantum. There are reasons why it will be high, but I don't want to discuss because it will take long time. So it'll as you increase the concentration, that temperature will decrease. So that means there is a phase transition at this point. Then there is another thing which is spin glass, which I said second one. When you have a spins more than 5%, then what you will see is that transition spin glass transition pressure will start increasing. It starts going up, and then at percolation threshold. Percolation threshold means that means there are clusters formed, and each cluster can see magnetic cluster can see each other. They can interact with each other. So at that point we call the percolation threshold. At this point, you will see the spontaneous magnetation. Long range order, spontaneous magnetation you will see at that point, and that from there it becomes stronger and stronger magnetic material. Stronger material means it becomes a ferromagnetic material or ferrimagnetic material, whatever. So, but in this material, what you see is that there is split symmetry. The curve is a just parabol, so in perfect symmetry. Now, if you have r less than two stages means it is the material can exist two positions. That means first one, paramagnetic state perfectly symmetric, and this is not non-symmetric. That is symmetry breaking. Suppose if you go non-symmetry, symmetry breaking, we say that. There are two states. You know that when you choose the magnetic material, if you take a ferromagnetic material, and if you do with the field as a function of field, if you do, what you will get is one maxima, one saturation, another saturation, another critical experiment that is zero point 0.5. So we saw gamma and beta, these are the two critical experiments which can tell you whether the uh, tension is first order or second order. And these are the different models, the mean field theory and 3D Eisenberg and 3D Ising models. And there are theoretically it is calculated. These are the models which give you for the second order tension, you will have this kind of critical experiment. If you have a mean field theory, that means there is no disorder. If you don't have disorder, then you will have these are the critical experiments. So you can analyze your magnetic data and see whether these critical experiments are coming or not. If they are coming, that means you have perfect good mean field theory can explain your data. On the other hand, 3D Eisenberg, if you have a disorder in the material, then you will have these critical experiments. Now, if you are given a material, magnetic material, the transition, whatever you observe, whether it is perfectly ordered or disorder, you can identify immediately by doing the magnetation measurements and using this theory. So the correlation. So what we have done is we have taken one sample as just for the example, one sample as shown. This is what I am saying that the magnetation as a function of temperature, as a function of field. This magnetation as a function of field, and if you see this this kind of thing we have plotted as the array plots we call. From there we can extract the spontaneous magnetization. Spontaneous magnetization, once you extract, this is what the array plots, modified array plots. From there you can extract the spontaneous magnetization, and if you plot spontaneous magnetization versus temperature, you see at the point of critical concentration that magnetization disappears. So the at critical temperature, the spontaneous magnetization disappears means the ferromagnetism goes away. Above that, it is a paramagnetic material. So this kind of thing, it shows the critical exponents. If you see that beta is 0.37 and gamma is 1.3. Gamma should be 1.5 for mean field theory, and then Heisenberg model it should be 1.3 or something like. So there is a strong disorder in this material. I can say that, and it's a second order phase transition. I can identify clearly. So this is the analysis one can do. So now, so far I have discussed about the classical phase transitions, and I have shown what is the first order transition, how to identify first order transition, second order transition, first order transition, second order transition, even by looking at discontinuity and also phase mixing, one can say. Second is that you can also find out the critical exponents and say whether it is first order or second. Now, the quantum phase transition is the main topic for me. So, the quantum phase transition, actually, the classical phase transition is coming from because of the thermal fluctuations. What are thermal fluctuations? That heating up and all thermal fluctuations it is coming. So that is giving us the classical phase transition. But in quantum phase transition, uh, we have to go to lowest temperature because we have to suppress the thermal fluctuations. Then we can see the quantum phase transition. Quantum means it's temperature transition. At zero temperature, you will have this kind of whatever transitions I observed. I said earlier, those transitions you can observe. Earlier, the thermal fluctuations in the classical thing, you have thermal fluctuations. In quantum phase transitions, you will have quantum fluctuations. What are quantum fluctuations? You have to go to lowest temperature, T is equal to 0. These are defined as T is equal to 0 Kelvin. But experimentally, we cannot go to T is equal to 0 Kelvin. Experimentally, we can go to now recorded temperature 36 Kelvin, 38 Kelvin. But experimentally, if you want a certain volume, if you want to check, you can go up to 6 microkelvin or so something. So lowest temperature we can go down to 6 millikelvin. And if you reduce the temperature, T is equal to 0, T is equal to 0, KT is 0. Thermal energy is 0. That means atoms are all classically, atoms are stable. They are not moving at all. So therefore, there is no kinetic energy. But that is what classically we say that there is no kinetic energy. But quantum mechanically, at E is equal to 0, T is equal to 0, the energy is not 0. Because there are quantum mechanical fluctuations. As per the Heisenberg uncertainty principle, we know that delta position uncertainty and momentum uncertainty is a constant. The multiplication of these two is constant. That is, delta x is position uncertainty and delta p is the momentum uncertainty, and that is equal to product of these two is equal to h by 2 pi, constant. So if I say that the kinetic energy is going to 0, that means the momentum, the uncertainty in momentum is coming down 0, come to low. And that means this has to increase, delta x has to increase. So delta x has to increase means the atom can be going from one place to other place. So the oscillating, it is oscillating. So these are called fluctuations. And these fluctuations, any oscillating body will give the energy. So this is also called 0 point energy. We learn in quantum mechanics, quantum oscillator analysis. You will see that kind of 0 point energy. At t is equal to 0 also there is some energy which can contribute to the various effects. So at t is when t is equal to constant, now you can ask me when t is equal to constant 0, how can we get the transition? But the operating parameter here is P, H, and X. P is what? Pressure. H is field you can use to get the transition, and X is the composition. Composition is just how I said no gold. In gold, I am adding iron. That is what the composition variation. And H is when you apply the magnetic field on a particular material, then it can go to one phase to other phase. Similarly, we have seen in the first slide, when you change the pressure, a liquid can go into solid state. Similarly, you can also use in magnetic material a pressure which can go from the one state to other state, phase transition into state. So, if you see this one, this is a muon. Muon is nothing but muon resonance. Okay? Muon spin resonance we call muon. So, with that you can measure what is the fraction of magnetism present in the material. Okay. So now you have, when I apply the temperature and measure the fraction of the volume fraction of the magnetic moment, you see that when pressure is zero, you will have almost one, and which is going to Tc is about 30 Kelvin for this particular sample. The sample is ZR2 and MNF. This sample is MNFS, which is called a miscellaneous material. And now if I increase the pressure, if I keep on increasing pressure, you have to see that different pressure, the Tc is decreasing, and finally at this point at 15 kilobar, the magnetism disappears here. The magnetism disappears. So here you can see there are two phases. A fraction of one magnetic phase and fraction of non-magnetic phase also will be present. So this fraction is decreasing, magnetic fraction is decreasing as you increase the magnetic field. So you can see that magnetic field pressure, this pressure versus magnetization I have put here. So you can the magnetization decreases and suddenly it falls. This is the type 1 first order transition. This we call a first order transition. Now this is typically continuous. This is second order transition. And if disorder is there, in the pure sample you will get first order transition. If disorder is there, then you will have a continuous transition like this. And at this point, you will see that the magnetic clusters, because of the disorder, you will see the magnetic clusters are spin clusters in those parts. Those are the places where the quantum phase transition is also observed. So there are different kinds of things, transition. I think because of paucity of time, I will skip that one. And then outside now, right? So now this is the one final. Now this is the finally I will just discuss. I have a lot of data, but I have gone slowly, very slowly. So this is the typical phase diagram for the quantum phase transition. This is R is either P or H or X. These are either pressure or field or X. X is the composition. I vary these parameters in this axis, and in y-axis I measure the temperature, transient temperature. So at T is equal to 0 or P is equal to 0 or H is equal to 0, I have a transition there, Curie temperature there. As I apply the pressure, more and more pressure if I apply, then the transition comes down, transition comes down and becomes 0 here. And transition 0, this is what we call quantum critical point, quantum critical point vector point. That is quantum, if I change x, this is the quantum critical point, x, this composition, I am getting this as a critical concentration, quantum critical concentration. That means that T is equal to 0, if I prepare that concentration, that will have a quantum critical behavior. Quantum critical behavior, this quantum critical behavior, if I want to study, and I have to, in this figure, if I see, I have to go to T is equal to 0. But if I see this yellow region about temperature, in this region which we call as a, where kT is close to H mu C, H cross mu C, that is energy, thermal, that is the fluctuation energy. And this is the thermal energy. So in this region, if I study the material, this temperature region, I can say whether it's a quantum critical point or not, or quantum phase transition or not. So for that, you have to verify these things, Fermi-liquid theory and non-Fermi-liquid theory. And this is a little bit involved. Fermi-liquid, I just now said, Fermi-liquid is observed generally in the pure materials, and non-Fermi-liquid behavior is observed in the quantum materials. And these are some of the data I have taken here. So there is no time to show all this. we have done some experiments in this. So the magnetic, if you see that this is what the incident behavior will show that the magnetic material has certain properties which shows, and this is a non-Fermi liquid behavior. You see that here is completely almost straight line at this point, 12.5, x is equal to 12.5%. It's almost straight line. Here there are bends are there in this case. So at this point, we have a critical point, quantum critical point at this concentration. That means this sample will exhibit a quantum critical behavior. So you can, that is what non-Fermi behavior. Non-Fermi behavior, and you can see that an exponent is the exponent. Resistivity we have fitted to this equation.
Any questions?
Yeah, yeah. No, this is what the continuous research we are doing right now. But this can be, I said in the first beginning, I said that it can be in future. Quantum now, quantum information and other things are not from qubits and other things. Now I have discussed about maximum only. This kind of work is also done in superconducting. Superconducting bits, quantum bits, are used for the quantum observation. Yeah. Yeah. Yeah, yeah, yeah. So I'm only discussing about magnetic fields here, no electric field. So the electric field is the resistivity I mentioned. It's not a field. Electrical resistivity, that means how freely electrons are going through the solid. That's what we are saying. Basically, I'm studying here electronic properties. Electronic properties are linked to both magnetism as well as resistivity. Electron behavior. Electron behavior in solid. Electron can have magnetic moment, also charge. So the charge will give me the electrical resistivity, and magnetic moment will give the magnetic property. These are the two properties I am detecting here to derive what kind of, whether it is conventional behavior or it's unconventional behavior. At particular composition, I am seeing an unconventional behavior, which is, I said, that non-Fermi liquid behavior, or some such kind of. So this is a strongly correlated system. People behave coherently. There will be turbulence. I cannot say that, because this is coming at 0 degrees Kelvin, and 0 degrees Kelvin quantum fluctuations only will be there. Any electric field in thermal fluctuations also will be there, any temperature. Here I'm talking about only at 0 degrees Kelvin. 0 degrees Kelvin, there is no thermal fluctuation.
Now we proceed on to the National Day program that commences within few minutes from now, celebrating the spirit of science through various academic and cultural activities. Before that, sorry, I request Principal Sir to please come on the dais to present the moment of honor to our speaker.
Sir.